Okay, let me share a screen. So I don't want to share the screen. Come on. Okay. It is sharing the screen, but that's not really what I wanted. I want to share the whiteboard. Share content. Come on. Sorry, whiteboard. How are you today, by the way?
I'm all right. Tired.
Okay, good. Oh, I'm sorry to hear that. I'm a little tired too. Classes or just life?
Classes specifically.
Classes have a tendency to do that, you know? All right, so all of these questions that I was going to work on continuity are from like old homework. So if you wanted to see the questions themselves, you can go to Moodle and you can look at old homework and you'll see like I don't know. I think it's, let's see, it's homework 9, continuity.
Right.
And so I'm going to start on number 1, and then I'm going to kind of skip down a good ways. So you know, I've got a calculator here. I actually don't know, and you can tell me this, like I have all the answers in front of me, so I could use those, or I can just do it with a calculator. Sometimes I like to do it with a calculator because it slows things down a little bit. Kind of lets the students kind of, you know, like stop and go, okay, well, he's punching that in a calculator. I'm thinking about the numbers and whatnot. So you just let me know. All right, so the first one that I'm going to do number 1. So this is like, so if you want to find the problem itself, it's homework 9, continuity. And this is like under old homework on the Moodle. So I'm going to do number 1 first, because just kind of helps to get into the right mindset here. So it says oil having a specific gravity. So the specific gravity of oil in this case is 0.9. Oil is usually somewhere in the 0.8 to 0.9. So it's like slightly less dense than water. Throws through a 4-inch diameter pipe. So diameters of pipes are either written as phi or D. I like to use the phi only because some people do. I don't particularly like it, but I use it just because, yeah, you know, just in case, so people will know what that means. And then it's got a mean velocity in that pipe. Velocity is usually written as U, and the overbar means mean. So the mean velocity is 8 feet per second. And this U just means velocity in the X direction. So that's what's given. And then required, we want to know, what is the volumetric flow rate? So volumetric flow rate, so that's a Q. And we want that in CFS and GPM. Okay, so it's gallons per minute. And then the mass flow rate, which is written like this, m dot. Okay, and they want that in slugs per second. I'm going to assume that you, like everybody, is not happy when the slugs show up. That's pretty normal. However, just think of it as being no different than kilograms. Like if I had kilograms per second, we're just using a different system. Okay, so so the way we do this is we have to think about Q. Okay, and Q equals, really technically it's integral of the velocity, which in this case will be U times dA. It's technically how we would define this, or really it's actually that's even a dot product. And we're integrating over the area. In this case, however, they don't tell us anything about this thing varying over an area. They just gave it to us as an average velocity. So in that case, if you have an average velocity, you can change this and you say, you know what, I don't want to deal with that integral. We're just going to make it the average velocity times the area. Okay, which is like a lot nicer. You know, if you get that, you should be very happy. Okay, and that's actually most of the time what we'll do here. On tests, sometimes I like to give you something with an integral just to make sure that you know how to do it, but it's just kind of like a once in every now and then thing. Most of the time we deal with average velocities. So once we get that, this is really not too involved. Okay, we've got a U right here, a U bar, that's 8 feet per second. And we've got an area. Now, my area I went ahead and converted to feet because, I mean, that's just the easiest thing to do. So the formula for an area that we use in this class almost always is pi times diameter squared over 4. You're used to pi r squared, but most of the problems here give you diameter. So it's easier to just get in the habit of using this. So that's what we're going to use here. So pi times the diameter in this case is a third of a foot. We'll put the foot in there, squared. Okay, and we'll divide by 4. Okay, and that's how we get an answer. Okay, noting that we've got feet squared times feet, so we've got feet cubed over seconds. So if we multiply that all out, I'll do the calculator here, although I don't think you need to. I don't think you need to see me punch this in, but we'll go ahead and do it. 8 times pi divided by 4 times 9 divided by 36. So that's 0.69813. 813, and that's cubic feet per second. Okay, and if we were to box that, we would go 0.698 CFS. Okay, 3 sig figs. Okay. Now, this particular question, I didn't write this question. They wanted in gallons per minute. A little bit annoying. Okay, that's because that's like high school stoichiometry. So 0.69813 cubic feet per second. Now, if I were to do this to you on a test, you would just look up the conversion rate from cubic feet to gallons. You don't have any idea what it is?
I have no idea.
Can you imagine? Can you guess? Like, think of a gallon of milk and then think of a cubic foot. How many gallons in a cubic foot, you think?
I couldn't even guess. Maybe 2.
That's probably what I would have guessed too. It's actually surprising to me. So 1 cubic feet actually has 7.48 gallons in it.
Oh.
To me, it's pretty surprising. So from that knowledge, you could actually pretty easily figure out how much, because you know the weight. It's 62.4 pounds per cubic foot. So you could very easily calculate how much a gallon of milk weighs, or a gallon of water, a gallon of anything that's mostly water. Okay, so that will get a gallon, and then to get this into minutes, we would do like this. Okay, so now we'll get gallons per minute. Okay, so we'll take that number, multiply times 60 times 7.48, and we get 313.32. 313.32, and that's gallons per minute. Okay, or 313 GPM. Okay. And this is really a nasty unit, so like we don't really ever really want to do that if we can avoid that. So that's no good. Actually, let me bring up Zoom here. Maybe I can. Oh yeah, I like having Zoom on 2 screens so I can see what it looks like. All right, so let's see. All right, so the last thing is m dot. So anytime you want the mass flow rate, m dot equals rho times q. And if you can't see that, just think about it as like, all right, this is how many cubic feet. Oh, feet cubed. Where's my eraser? Just to give you like a little intuition here, this is how many feet cubed we're getting every second. And we're like, well, okay, but I want to know how many slugs per second. Well, then for every feet cubed, how many slugs do we get for every feet cubed that are coming in? Mm-hmm. Right. So if I'm getting 20 slugs for every cubic foot coming in, and I've got 5 cubic feet per second, well, I just multiply 20 times 5, and then I've got 100. Does that make sense?
Yeah. Okay.
So this should be fairly logical. I mean, and of course, stoichiometrically, it works out because we get slugs per second. So then we need to do rho. So the rho for this oil, well, that's SO times the rho of water, right? And then this is Q. So we can do that by SO, which is 0.9. What's the rho of water?
64.2? Or am I thinking about specifically?
You're thinking of 62.4, but what are the units on the 62.4?
Pounds per foot cubed, right?
Right, pounds per foot cubed. Is that what we want here?
Oh no, we want slugs, right?
This is gamma. Okay, this is like the most missed thing on anything. So, so how do we go from gamma to rho?
We multiply by specific gravity, or we multiply rho by specific. Wait,
Okay, what's gamma equal?
rho over the rho water.
No, this is specific weight.
Oh.
So what is gamma? So gamma is rho g.
Oh,
So if I want rho, what do I do?
divide by gravity.
Divide by gravity. So what's gravity in this system?
32.2.
32.2. Okay. So this is what you need to do if you can't remember. Okay. So if you divide by 32.2, you're going to get usually we just use 3 significant digits on this, but rho equals, well, so that's if we divide by gravity. So yeah, I like my equations to be equations. So there's rho. Okay. So if we divide to 3 sig figs, it's 1.94. And this becomes, so a pound divided by a foot per second squared, all of this, that's a slug per foot cubed. Okay. So that's what we want to plug in here for the row of water. This is for water. Okay, 1.94 slugs per cubic feet. Okay, so it's always, especially in fluids or thermo, if you ever have thermo, it's very good to like just keep track of your units.
Mm-hmm.
Okay, and then we multiply that by my rho, which was right here, this number. Okay, 0.69813 cubic feet per second. Okay, a little sloppy because we're out of space. Okay, so m dot equals whatever the calculator says that is, right? So take this number times 1.94 times times 0.9 equals 1.2189. Okay, and that's slugs per second. Okay, so m dot equals 1.22 slugs per second. Okay, and that's how we solve it. Okay, questions? All right, let's move on. Okay, let's clear all that. Okay, what I like about this stuff is, well, we can think in terms of, let's see. Okay, so so if you've got that thing open, I'm gonna go down to problem 6, since that'll have some integration involved in it. Okay, so this will be 6 on the same thing. Okay, now you have these solutions if you don't feel like writing any of this down, but it says water flows through a 50 centimeter tall. Okay, so this is a conduit, and it's just like a square conduit, and it's 50 centimeters tall, 50, and 30 centimeters wide. Rectangular conduit, and provides a velocity profile described as, so this is like the water's going into or out of the board in this drawing, but this will be from the side view, and it's kind of flowing like this. Okay, and it says has a velocity profile, which they call capital V, equals 20 y to the half. Okay, and they put meters per second out here, which is a little bit annoying, makes the units a little weird. That 20 has units on it, which I'd have to think about what those units are. What would those units be? Y is meters. So that 20 has units of meters to the half per second. It's pretty annoying. Anyway, I'm gonna go ahead and, okay, because we're gonna get rid of that. This is meters to the 1/2 per second. Okay, times y to the 1/2. Okay, that's just because not having the units right is gonna aggravate me. And this applies to the top or the bottom, but not both of the conduit, half of the conduit, but not both. This is a terrible question, by the way, or a terrible way to write this, because it actually doesn't work. If you were to plot y to the 1/2, it actually looks like, or something like this. If you were to plot that, it looks like this actually. So in many ways, this is kind of the opposite of what we need. I need to adjust this equation, but let's just roll with it for now. You know, and this would actually keep going like this. So I need to adjust this equation, but I haven't done that yet. So, but we're just going to roll with it. So pretend that this looks like this. Okay, it doesn't. Okay. Assume that the profile is the same over the entire 30 centimeter width. So basically this shape right here applies right here, it applies right here, it applies right here, it applies everywhere across this thing. In reality, there's friction near these walls, which is going to cause it to slow down near those walls. But you know, whoever wrote this didn't want to deal with it. Okay, so that's what's given. And then required is A, volumetric flow rate, A. Q equals what? And then B, the mass flow rate, M dot equals what? And then C is the mean velocity profile. So we're going to call that V bar. Anyway, you can probably hear my dog licking at the screen door right now. I don't really know what his problem is. All right, so we're going to solve this the same way we did the last one. Okay, except it's just going to be a little bit more complicated. So Q equals the integral of, in this case, V dot dA. Okay, do you have any idea how to deal with this dot product or a dA?
Would it be a double integral?
Yeah, it's a double integral. Okay, so a lot of times we would say, well, Q equals, we'll integrate twice, V dot dx dy. Any idea which one of these we want to do first?
I have no idea. Maybe X? Or
Why?
no, Y.
Why?
Because our velocity is given with a Y in it. So
Okay, I mean, yeah, you've got the exact right idea. The thing is, so our velocity varies in the Y, it doesn't vary in the X. That's the key. So the X direction is really easy. The Y direction is not so easy. So the order actually doesn't even really matter. But the X direction offers, basically for the X direction, all you have to do is multiply by the width because it's going to be the same straight across. Okay, so let's do Y first. Let's do the more difficult one first. Okay, so I'm going to switch this order here. Boom, boom. Okay, so we'll go Y and then X. So then we can plug this in. So V dot, well, let's plug in what V actually means here. So V is 20 meters to the half per second. Okay, and we're going to dot that with dy. And I'm going to put this dx like way out here because I don't feel like dealing with that just yet. Okay, any idea what the limits of this dy are?
No.
Okay, it's a little bit complicated. Okay, so when you have limits, we need to think about where does it start and where does it end in the y. So what's the first y that we might want to use? So first we have to define, like, well, this is the, unfortunately, I guess dx dy. So I guess this is x direction. This is the y direction. So if I use that as my coordinate system, where does y begin?
0.
Yeah, perfect. Perfect. Okay, where does it end? This is a trick question.
25 centimeters.
Yes, perfect, right? Because it only applies to the top or the bottom, right? So 25 centimeters. So 0.25. Okay, now how do we deal with that dot? Do you have any idea?
No.
I hated dots when I was a student. I still don't really like them all that much. Hold on, I gotta get some fan going here. What the dot means, and this is not really that complicated. Do you remember what the formula is for a dot product?
It's been a while.
Okay, you're right, of course, because this is what happens. I'm currently teaching them in, so let's suppose we have A times A dot B. These are vectors, right? Okay, so what you do is you take the magnitude of A, you multiply it times the magnitude of B, and then you take the cosine of the angle between them. Or is it the sine? I think it's the cosine. Okay, is it the cosine or the sine? Give me 1 second. This is what computers are for, right?
Yeah.
I guess it depends. I think of it as the sine. Let's see here, dot product. Yes, the cosine. Okay, so, and I'm gonna teach this to you right now, and I think hopefully you'll never forget kind of what it is again, or like why it is what it is. And what we're talking about here, like in this, and it's going to apply in this case, is what we're talking about is, so we've got an area vector. So let's suppose I've got a pipe or something, and I want to know how much fluid is coming through it. So the area vector, if this is the opening, or like this is the side view of this pipe. All right, this is a random pipe. And so it's got an area A. Well, how do I define the area A? Well, it's a vector going outwards from that opening. So this is A is the vector. And if you think about it, you're like, well, why is the A vector defined perpendicular to like the area? Well, because I can't really very well define it as up or into the board. It has to be perpendicular to the area. That's the only direction that makes sense, right? So then I've got a B. B is, say, the flow through this thing, right? So B is the flow through this thing. Well, if A and B are the same, like if the area vector and the B are the same, well, then to figure out like the volumetric flow rate, well, I would just do the area times the velocity, and that's great. However, if my velocity vector is on an angle, all right, let's imagine my velocity, we're coming off at an angle like this. Well, not all of that water or whatever it is actually going through the opening. Some of it is just kind of sliding along the opening, right? It's not actually crossing that boundary.
Yeah.
So we only care about what's crossing the boundary. So we only care about this right here, right?
Yeah.
And so that much is going to be the magnitude of B times the cosine of that angle.
Mm.
Okay, so that's where this annoying formula comes from. Does that make sense?
Yeah, that makes sense.
Okay, so we have a dot product here. So basically what that dot tells you to me is when I see the dot, it tells me, because I don't remember this formula. I don't care about this formula. What I think immediately is that dot product tells me that the only thing I care about is how much of this velocity here is actually crossing this area that we've got over here. Okay, and so when I look at my picture, basically what I'm asking is all this flow perpendicular to this area? And if it is, then I can erase that dot and make it a multiply. If it's not perpendicular, then I can erase the dot and make it a multiply, but then I have to take into account the angle. So I have to put a cosine in there. Does that make sense? And my hope here is that you're getting a little bit more sense of like this annoying formula, like where does it come from? Because I don't remember it. I just see the dot product and go, okay, I need to think about my angles here, right? Because it could easily give me a different angle. Like if it gave me this angle here, then it's going to be a cosine of that angle, right? I mean, excuse me, a sine of that angle, right? But of course, this formula is okay because this data is technically defined as between A and B. So the formula still holds. But anyway, am I making any sense? Am I just jabbering on?
Makes sense.
Okay. So in this case, what we can do, because these things are like, because this is perpendicular to this area right here, we can basically just erase this dot and treat it like it's being multiplied, which is good because we know how to do that, right? So let's go ahead and do that. Oh, we forgot one thing. If I only go up to 25 centimeters, what else do I need to do? Because I haven't taken into account the top half. So how do I take into account the top half?
You multiply it by 2, the whole integral.
Yep. So we're going to put a little 2 right there. Okay. So now we've got the top and the bottom. Okay. So once we've done that, this should have 0.25 meters. So once we do that, we're just going to integrate. So 20 meters to the 1/2 per second. What happens when we integrate that?
It gets what happened to the y to the 1/2 power at the top?
Oh, thank you. Thank you. That makes all the difference. Okay, y to the 1/2, right? Okay, so what happens to that y to the 1/2?
Oh my gosh. You add one to it, so it's gonna
Y.
be 3/2,
Mm-hmm.
and then divide it by the whole thing by 1/2, right? Or by
We're gonna have a 2/3. We're gonna have a 2/3, right?
oh yeah.
Okay, so we're gonna have a 2/3 out here, and then we've got a 2, and then we've got a dx out here, and we've got an integral here. Q equals. Okay, so let's go ahead and simplify that because that's a little bit annoying. So we've got 4/3, 80/3. All right, that's a lot of stuff. 80/3 meters to the 1/2 per second. So I got 80/3 meters to the 1/2 per second. I can't get that 3 in there because it's kind of like stupid. Can you just let me use all the screen? Okay, and then we've got an integral y to the 3/2 dx. Okay. What are the limits of this integral?
I have no idea.
Well, what did we do for x's? I mean, for y's, we went from where it starts to where it ends. So where does it start?
So 0 to 30.
0 to 30, right? So q equals integral from 0 to 0.3 meters. Okay, notice I'm being careful with units here. Like I'm not using centimeters because that's just, to me, that's just asking for a potential problem. We just don't know. Oh, that's a 3 on the bottom, sorry. So I'm gonna put a 3 right here, meters to the 1/2 per second. Okay, so actually, sorry, the integral's on this side because we already brought that out. By the way, you're very good at calculus. I sense that already. You know, maybe you don't remember the power rule, but you've got the right ideas, which is the most important thing, which everybody often forgets. Y to the 3/2 dx. Okay, so how does that vary with respect to x? So if we integrate that, what do we get?
It's just a constant, so we just add on to it. Add on to x.
That's right. That's right. So we get y to the 3/2 times x from 0 to 0.3 meters. And then we've got this 80 meters to the 1/2 per second over 3. And so now we just basically we're going to multiply the whole thing by 0.3 meters. Right? So we'll end up with what's 88 times 0.3. So that's what, 24. So 24 over 3, which becomes 8. Perfect. Nice, clean number. So we get 8 meters to the 1. Oh, no, that's meters to the 3/2 per second. Wait, do we ever plug in our y? We didn't plug in our y's, did we? Dag nubbit. All right, let's step back a bit. I was like, this is kind of weird. Let's go from 0.25 meters to 0 right here. And I'll go ahead and plug that in with my calculator here. 0.25 to the 3/2. I'll do 3/2. 1.5. Okay, times 80 over 3 divided by 3. Okay, so right here, I'm going to erase all this, but all that work we did was correct. We just forgot to plug in the limits. So basically, what we've got here is 3 1/3, so 10/3. And if we follow the units, we're at meters squared per second. Okay, so we can go up here and we can kind of do that up here. Okay, sorry about that brain fart.
It's all good.
Yeah. You know, it's calculus to me is really fun when it has a physical meaning. Okay, so 10/3 meters squared per second, and as you said, that's a constant in the x, so it becomes 10/3 meters squared per second times x. So when we plug that in, we can multiply that by 0.3. So times 0.3. Okay, and that comes out nice and pretty to 1. Okay, and if we plug the units in, we'll get meters cubed per second, and we'll subtract off the 0, which is, trivial. So Q equals, sorry, I lost my Q's on this side. Q equals 1 CMS, cubic meter per second. Okay. And I'll make note of this because this throws my students for a loop. When I have CMS, they think centimeters per second. So nobody ever writes CMS. If they wanted centimeters per second, they would do centimeters per second. But this is cubic meters per second. Okay. The key here is to note that this is a Q. If you've got a flow rate, it has to be volume per time. The more common one, especially in this country, is CFS. So like if you were to like look up right now, you know, the flow rate of the Mississippi River, if you were to go to the USGS website and they'll tell you what it is, like right at this exact moment, and they're going to report it to you in CFS. So right now we're probably at 500,000 CFS. It almost seems like we should have a different unit than, because once you get up to into the 500,000s, you're like, can we get something that's, you know, basically the Mississippi River varies from about, I don't know, maybe on the low end, it probably goes down to about 300,000. And on the high end, it goes over 1 million. And maybe in like a severe flood, 2 or 3 million, where like, that's like where we're like terrified that, you know, cities are gonna, I don't know. I'm not exactly sure what those numbers are, but it's something like that. Anyway, questions?
No.
Okay, I mean, I don't know if you're at all interested in rivers. If not, I won't mention too many more rivers. To me, it's the thing that keeps me in engineering is that I love rivers. So I'm more of a scientist than an engineer in some ways because I've never engineered a river, but I've studied quite a few. So, but everybody has their angle, right? Some people are like, I don't care about any of this. I really like soil. And some people are like, I really like, you know, water treatment, or I really like, you know, structures or whatever. So you're civil?
Mm-hmm.
Okay. Do you have any idea what direction you want to go with it?
I'm not sure yet.
Okay.
I'm taking a geotechnical engineering, so I'm just getting into like the soils part of it and structures at the same time and this, so it's like, I guess 3 different areas. I'm not sure yet.
You actually get it. It's the thing that kind of stinks is that you don't get into the interesting things until you're so far into it that if you don't like them, you're like, well, what do I do now? Hopefully you're liking them.
Mm-hmm. Oh yeah, for sure.
They didn't teach me when I did this, they didn't teach me enough about rivers. And so they taught me all about water treatment, which I actually find very fascinating, but I didn't like the idea of going to go work at a water treatment plant. And I really found structures very interesting. And
Yeah.
I was like, oh, but then I was like, I thought about it and I was like, I don't really want to be a structural engineer, even though I love it. It's just not really the thing for me. And it wasn't until I got to grad school and they were like working on rivers and natural systems. And I was like, no, this is it for me. This is what I love, you know? So, so we each find our own little niche, right?
Yep.
And I can't make everybody love what I love. So thankfully. All right. So I've got a few more. I think maybe before we do an engineered solution, because we just talked about a river, let's do a river one, because this is one that I came up with that I really love. Let's not do that one. Let's start with an easier one. Let's start with number 7, and then we'll go to the one that I love. Okay, here we go. 7 on that same problem set. Okay, 2 pipes are connected to an open tank of water. Okay, this one actually has a typo in it. Okay, so basically it looks like this. We've got a tank of water, and it's got some pipes coming in the bottom. Okay, it's got pipe A and pipe B. I've asked a version of this on an exam like 10 million times. Can you please let me erase that, you jerk? Okay, thank you. Okay, so we've got a pipe coming in. This will be pipe A. This is pipe B. And this is water. The typo is it says water at 10C. This actually should be 10F, or really it should be 40F. So we'll call this water we'll make it 40F. Okay, it doesn't really matter. I mean, it does because it changes the density of the water, but we don't, Anyway, water enters from the bottom of the tank at pipe A at 9 feet per second. So we got 9 feet per second. And the level of the tank is falling at a rate of 1/2 inch per minute. Okay, so this thing right here is falling at 1/2 inch per minute. Okay, I don't want to deal with inches per minute, so I'm going to go ahead and adjust that right now. Okay, I'll consider that one of my givens. So 0.5 inches per minute. I mean, that's a horrible unit. So I'm going to multiply that by 1 minute, 60 seconds, 1 inch. This is 12 inches, 1 foot. So basically it's not falling very fast. Okay, because I have to do a half divided by 720. So 0.5 divided by 720. Yes, a very small number, 6.9444 times 10 to the negative 4 feet per second. And of course, that's why we use these horrible units, is because it's something we can picture. Whereas if you told me this, I'd be like, I really have no idea what that means. Okay, so anyway, that number goes right here. So let's just call that, what do you want to call that?
I have no idea.
All right, well then let's leave it like that. And I'm gonna, when we get to the equation, I think you're gonna see where it goes, and there is a good thing to call it. Okay. I want you to think in terms of calculus. Okay, and I'll leave it at that for now. Okay, assuming that the tank has a cross section that is 8 feet by 12 feet. So the top of this tank, okay, if I were to draw it in 3D, okay, this is going to be 8 feet. This is going to be 12 feet. Okay, what is the velocity in pipe B? So required is VB equals what? Did it say anything about? That's interesting. Oh, okay, it does give us the diameters. I was like, we must have the diameters here. So diameter A is 8 inches. Okay, so that's 2/3 of a foot. Okay, again, I'm not working in inches. I guess I could have in this problem because everything is given in inches, but I chose not to. So this is 5/6 of a foot. All right. So this is so required is VB equals what? Okay, one thing I will note about VB is we don't know if VB is going in or out. What does your gut tell you about VB? Is it going
right?
What's that?
It should be going out.
How do you know?
Because the water's sinking.
Right.
Water level sinking.
Right. So essentially it has to account for it. Like both of these things tell you that should be going out, right? We've got water coming in and the level is dropping. So both of those should be encouraging water to leave at VB, right? So did you watch my video on conservation of mass?
I don't think I got to it yet.
Okay. So here's how we're going to do this. This is how I like to do these things. Okay. I think about conservation of mass. I had a professor that always taught this way, as what goes in. What is what goes in equal to, do you think?
Would it be the 9 feet per second?
Right. So that's going to be when I work downwards. But I mean, what other concepts should it work into? Should it go into? So like the mass that goes in equals, like if I wanted to figure that out, how would I figure it out? What the
would it be like how we do weight equals specific gravity times volume, but not?
I mean, you're thinking in the right idea, but okay, let me just conservation of mass. Okay, in a nutshell is this: what goes in equals what goes out, unless what?
Oh, okay.
Like in this case, what goes in and what goes out are not the same. I think we can agree on that, right? How do you know that they're not the same?
Because the pipe diameters are different. Maybe?
Yeah, but the velocities could be like, like the velocities could overcome that.
Oh.
Like I could easily have a pipe that went like this, right? And then what flowed in right here would equal what flowed out there, right? So this flow would equal that. But in this case, there's something else. Like you knew this was out. How did you know?
Because the water level was going down.
Right. So what was stored in the system was changing.
Okay.
Right. So that's how we know that what comes out is not equal to what comes in. In fact, what's leaving is more or less than what comes in. Do you know? It's okay. So this is what it is. This is how I do it. Okay. So in equals out plus accumulation. And I'll go ahead and write the full word here, accumulation. The accumulation in this case is negative, right? We have negative accumulation. We're losing mass, right? Okay, so what I'm going to do here, I'm going to draw a control volume. This is my volume, right? Yeah, let's not use blue. Let's use red. Okay, so we're going to think about, okay, and this thing is going to be right at the surface of the water. Okay. And what I want to do is I want to think about things that are crossing that boundary. So this 9 feet per second is crossing that boundary and it's going in. Okay. So we need the mass flow going in. Okay. So that means rho Q in. Fair, right? And in this case, we're going to call that A. But right now I'm just like expanding this. Okay, equals out. Well, we've got rho Q out. Okay, and then the accumulation term. So this is how much is coming in per second. This is how much is coming in per second. Actually, let's go ahead and develop this a little bit. So if that's how much is coming in per second, I want to know total that's coming in. Well, I need to multiply that by time. So change in time. Let me erase this so it looks clean and pretty. Okay, rho Qn. So that's like slugs per second in this case. And so if I multiply that by a certain number of seconds, that'll tell me the total amount of mass that flowed into the box, right? So we can do out, and I can say, well, rho Q out. Okay, I'm going to put that in parentheses, or I'm going to put the parentheses here for the in. Okay, out. Okay, and that's obviously the same amount of time. Plus, and then right here, I'm going to say the change in mass, okay, equals the total change in mass. Okay, and this should make sense to you. So, or hopefully it does. So what this says is, like, if I've got a certain amount of slugs per second flowing in for however many seconds, that tells me how much went in. This tells me how much left. And the difference between those is how much mass changed within my container.
Mm-hmm.
Logical?
Yeah, it makes sense.
Okay, so then what we can do is, well, this is fluids class. I don't like mass because, I mean, we're going to use mass, but instead of mass, I'm going to note that mass equals rho times the volume. Okay, because rho is mass per volume. So if I multiply times the volume. Okay, now what I'm going to do is, like, now I'm going to start making this specific for this problem. So I'm going to do a few things. First of all, delta T, I'm going to divide that by both sides, delta T. Okay, so now I've got rho Q in. And the reason I'm leaving it like this in is that for some problems, you could have multiple pipes coming in, and those would all be accounted for in this term. Okay, and this one's going to be rho Q out. And what does this one look like to you?
Which one?
This last term. Oh, not equals, plus. What does it look like? Does it look like something?
I feel like I should know, but
it's okay. In this case, I'm going to do something real quick. This rho is not changing. So I'm going to pull it outside this delta.
Okay.
Okay. So I'm going to get rho times the change in volume over T. Okay. Do you think the density of this water is changing from in versus out versus in the tank?
No.
No. Okay. So because it's incompressible, we're going to get rid of all of that. Okay. So if you have incompressible, you can get rid of the rhos.
Okay.
Okay. So now I've got Q in equals Q out plus delta V over delta T. What does delta V over delta T look like to you?
Change in velocity over
change
time.
in volume.
Oh, yeah, in volume. So it's kind of, it's like a flow rate.
It's kind of like a flow. It is, you know what? Okay. It is exactly like a flow rate. Okay. And there's another way we could do this. And I've done this before. So there's two ways you can solve this. One, so I could take my control volume and I could do a different control volume. Like, let's suppose I put my barrier here. Then instead of thinking about this right here, this dropping as a change in the accumulation in the system, I could just think of it as a flow rate going into my boundary, crossing my boundary. So that's another way we can do that. And we'll do it that way too, and you'll see it get the same answer. But right now I'm thinking about this as change of volume per time. Okay, and I guess what I was driving at is this is a derivative. Okay, if you do this on a small enough scale, you can make it like that. Okay, now it doesn't matter in this case because the flow rate is constant, but on other problems it might matter. How do we define this volume? If you want to define the volume of this thing at a moment, at an instant, how would you define it?
Oh,
of the tank.
We aren't given the height of it, so that matters, right?
Well, let's not worry about this particular problem. Let's just say you had a problem and the tank is a cube or a rectangular solid. How would you define the volume of a rectangular solid?
Area times height.
Or length times width times height or whatever, right? So let's do area times height. I like it like that in this case. Okay. Is the area changing in this problem through time?
Does it because of the pipes or no?
I mean, obviously when this thing drops low enough, it will. But when the water is still in the tank itself, it's always 8 foot by 12, right?
Okay, yeah.
So we can take that area and we can bring it outside. Okay, so we got Q in equals Q out plus area dH dt. All right, now, what do you think we want to call this rate right here?
Velocity, because we have height over time, so meters per second.
Yeah, or feet per second in this case.
Oh, yeah, yeah.
So what we're going to call it is we're going to call it dH dt.
Oh, okay.
Okay, does that make sense? So it's how much the rate of the water is changing per time.
No, yeah.
Okay, and we're going to do something else here. We're going to put a negative sign on it. Okay, because it's going downwards. Okay, so now we're ready for this problem. Okay, so I mean, I just derived a whole bunch of stuff. I derive it in the equations, but when I can actually talk to somebody, you know, it's a little bit more useful, I think. So what we're going to do here is Q in 9 feet per second. Feet per second. Okay, so Q in is that times the area, right? So we don't need to worry about that dot because because it's just going to be straight across it. So we got that, and now we need the area of that pipe, which is pi times the diameter squared. So pi over 4 times the diameter squared. So it's 2/3 squared equals the Q out, which we assume is out. So if it ends up getting us a negative number, that means it's in. Okay, so it's just like statics where you assume a direction. We're going to assume a direction here, so I would call this BB. And the area of that pipe is pi over 4 5/6 of a foot squared, like that. And then we're going to add the area, which is 8 feet times 12 feet. What is that? 96 square feet. Okay, times this number right here is my dH dt. Negative 6.9444 times 10 to the negative fourths, or negative 4, I guess, feet per second. Okay, and I'm assuming you don't need to see me plug this all into the calculator.
No.
But if you do, let's see what the answer is. I've got that open on another tab somewhere. Let's scroll down. It comes to 5.883 something. Looks like back in those days I didn't keep 5. So we'll say BB equals 5.88 feet per second. Okay. So the other way we could have solved this with N equals out plus accumulation is, and this is something that, so you notice the rows don't matter as long as it's incompressible. So as soon as we notice it's water, you can immediately think, okay, this is incompressible, which means the row is going to be constant everywhere, which means I could treat this like, well, row in, all the row ins equals all the row outs, okay, plus accumulation. And then what I could have said is, I want a different control volume. So I'm going to use this control volume. Like that. Hey. Okay. And then once I do, hey, shh, it's okay. It's okay. It's just a dog. All right. So then we've got this one going in. Okay. Q in. I've got Q out, we're assuming. And the way I've drawn it, this is not accumulating anything at this point. So what I'm going to do is I'm going to treat this like a Q in. Okay, so this accumulation goes away. I've just got two Q ins. And so in this case, I've got 9. I mean, it's mathematically, it's going to end up being exactly the same, 9 feet per second. Okay, times the area, which is going to be pi over 4, times the area of that pipe, which was 2/3 foot squared, like that. Okay, that's an in. And then we've got, this one is a flow rate in. So it's going to be that velocity, which I'm now going to treat as positive. So 0, no, let's see here, 6.9444 times 10 to the negative 4th feet per second. Okay, times the air, its cross-sectional area, which is 8 feet times 12 feet, right? That's that 96 square feet, 96 square feet. Okay, equals the Q out, which is going to be VB times its area, which is going to be pi over 4 times its diameter, which is 5/6 of a foot squared. Okay, and mathematically, if you look at that, you'll see this is mathematically identical to this equation right here. Okay, it's just this negative sign and which side of the equation it ends up on. Okay, so it's whether or not you think of it as accumulation or flow rate, either one. It's just kind of like what makes sense to you, like in your head. Okay, so it's whichever way you want to do it. Okay.
Right.
Any questions?
No.
Okay. All right. So we've got 15 minutes, so we may not be able to get to my favorite one. But that's okay. So let's go, because I wanted to do one where the density changes. So let's do number 8. Okay, because this is like pretty interesting. All right, so air at standard conditions. So this is number 8 on that same problem set. Air at standard conditions, 1 atm, so air. So given air at, so here we go. Let's draw the picture. So here's some kind of tank. So this is exactly like the last problem, except there's one kind of interesting thing going on here. So this is a compressor. So as soon as you see compressor and you see air, you need to note that the density can change. And probably that's the point of the problem. Okay, this is 2.4 inches, 2.4 inches. We hate inches. And this is 1.2 inches, 1.2 inches. Especially because they tell us that this is coming in at 10 CFS. And it gives us the density of this, which is 0.00238 slugs per cubic feet. Slugs per cubic feet. Again, we hate slugs as well, but unfortunately, there's nothing we really can do about it. This one, they say is 700 CFS. And they say this is got a density of 0.00350 slugs per cubic foot. Slugs per cubic foot. Okay, and the volume of this tank, VT, volume of the tank, is 50 cubic feet. Okay, let's see. And, okay, and what they want to know, so this is given, they're required, they say they want the average time rate of change of air density within the tank. Okay, so something equals 0. The average time rate of change of air density within the tank. Any idea what symbol that would have?
The what again?
Okay, the average time rate of change of air density within the tank.
Oh. I have no idea.
Okay, if I want the time rate of change of something, what does that look like in calculus?
Time rate. DT.
So we're gonna have a DT on the bottom. And we want the average time rate of change of air density.
Oh, okay. So D rho.
Right. And I'm gonna put a little T on there, just to remind me that's the rho in the tank. Okay. So, I mean, I'm trying to help, like, we never ask you guys to use calculus, but it helps to kind of like start, thinking along these ways. Okay. So, yeah. So anyway, so here we go. We got a solution. And what do you think we're going to do here? What kind of equation do you think we're going to work with?
N equals out plus accumulation.
Yes. N equals out plus accumulation. Where do you think the d rho t dt is going to come in?
I feel like that's going to be in the accumulation.
Yes, I think that's a really good thought process. All right, so the in, we've got an in, right? This is our in. This is our out, right? We've only got one in, we've only got one out. So let's go ahead and let's start doing it. So we've got, well, I'll just go ahead and do it. Rho Q in equals rho Q out plus the accumulation, which is going to be d by dt of mass, which is rho v. Okay, this one's not so nice as the last one because we're not going to be able to just get rid of rho because the density changes. So notice we've got a density here and we've got a different density here. So it's compressing it. It's like raising it from 0.00238 to 0.00350. Okay. Now, luckily, like that's not really a big deal because we just plug those numbers in here, right? They gave us those numbers, so it's no big deal. Now, this d rho t dt, that's going to come right here. We can see the d rho t and the dt, like we can see that right here. And we notice that the volume of the tank, however, is not changing. Okay, so that's where, that's where this all comes in. Okay, so you ready? Tell me what to write.
Okay. So we could, or no, we can't. So we'd plug in the rows, right?
Yeah.
In our Q's.
Do we know Q's?
Yeah, that's the 10 cubic feet per second and then the 700 cubic feet per second.
I actually screwed up. Let's forget that that's CFS. This is actually FPS. Sorry. So we can't plug that in, but we can get a Q from that, right?
Yeah.
Let's go ahead and get that Q. How do we get this Q over here?
Cubic feet per second.
We've done it several times now, but it is still new to you. Do you remember what Q equals? Look at your notes.
Oh, let's see. Okay, so integral of VDA.
Right, V dot dA.
Yeah,
Okay. Do you think we need to worry about this dot product in this case?
I want to say no.
No, because it's flowing out perpendicular to that area, so we don't have to worry about that. What about the integral?
I don't think so.
Okay, the only way we would ever deal with the integral is if they give us like a velocity profile like that. If they don't give us a velocity profile, we can't really very well deal with it. So what we're going to do is we're going to treat this like it's an average velocity. So we're going to say Q equals the average velocity times the area, like that. Okay, so basically we're going to say Q equals 700 feet per second times that area. How do we get the area?
Pi r squared over 4. Or was it d squared?
D squared, right. So pi d squared, which is going to be 1.2 inches, which is totally annoying. 1.2 inches is 0.1 feet. Actually, that's not so bad, is it? 0.1 feet squared divided by 4. Okay, so Q equals 700 times pi divided by 4 times 0.1 squared equals 5.49. 5.4978 CFS. Okay. So note here, we could have done it all in inches. I would just had to convert this to inches, right? And I didn't really feel like doing it because then this 10 CFS would have also had to been converted to inches. And this cubic feet right here would have also been converted to inches. So, it's kind of like, whatever you want to do. So notice that what's flowing out is flowing out. Q here is less than Q here. Okay. But the density is higher. So it's hard to tell whether or not what's, the density in the tank is going to be getting higher or lower because we can't really tell the mass flow rate really. But it looks like, if we compare CFS, this one is basically double of this one, but the density is not double. So it seems like what's in the compressor then is probably increasing in density over time. Just guessing. But anyway, so let's go ahead and do it. Tell me what to write down.
Like the values?
Yeah.
All right. So
plug it in.
We would start with 0.00238 slugs per foot cube.
Right.
And then we would plug in that first Q of 10 cubic feet per second.
Yes.
Which equals the 5.4978.
Yes.
Or we could do the density first too.
Oh yeah, well, yeah. That's fine. You're gonna switch order, I guess. And the density is 0.0
slugs per foot cubed.
Slugs per foot cubed. Okay, equals.
Should we or is that plus?
Oh yeah, plus, sorry. Yeah. Right.
Then we could just plug in like what we have for our required, right? The change in rho over time.
We can. But what about that VT? What do you want to do about that?
Should we just bring it out? Like, I guess maybe multiply it by T rho?
Perfect. Yep. Perfect. Okay. And note that this is gonna carry with it the sign. So it's gonna tell you whether or not it's increasing in density inside that tank or not. So we'll end up with, come here, D rho T. If, again, I'm assuming you trust me here. I put that negative sign here because I think I guessed a second ago, but I can't remember what the answer is. Where's these solutions? Oh, here it is. Okay. Oh, it looks like it's positive. Yeah. So it's, yeah, a second ago, I guessed that it was positive. Are you expecting a big number here or a small number?
I'd say small. I don't think it would change much.
Right, especially because we're talking about per second. 9.1. Well, here, let me get all the units, all the numbers here. 9.1154 times 10 to the negative 5. Okay, and the units here is basically the unit of density per time. So it's slugs per foot cubed seconds. Okay. So yeah, small number. Okay, so, is that logical? Makes sense?
Yeah, so that means that the density is increasing over time?
Yeah. Yep, by some very small amount because more mass is coming in than is flowing out. Ultimately, what will happen is if you were to, in a real problem, like a real compressor, I have to imagine that maybe you can force this amount of density in, but maybe not. Like what's going to happen eventually is as this gets more and more and more dense in here, it's going to start driving denser fluid out, or it's going to make it harder to push more density in here, more fluid in here, right? Because as this gets more dense, it's going to push back this way and that way a lot harder, right? But that's a different question entirely. So right now, this is just like the quote unquote easy problem. All right, so well, we've got like 2 minutes. Can I line up my favorite question just because I created it, and then we'll call it a day? Okay, it's my favorite. It's my favorite because I created it. So the last one is consider the confluence of the Yellowstone and the clear all drawings. I actually don't even have the solution on the thing, but so I said consider the confluence of the Yellowstone and the Missouri rivers. So here's the Yellowstone, and here's the Missouri, right? And they're just kind of like flowing upwards in my drawing as they flow upstream towards the Mississippi. Sally measured the river flow into the combined river and found that the Yellowstone, so here's the Yellowstone, and here's the Missouri. And so the Yellowstone has got a flow rate of 13,770 CFS. And the Missouri, so the Missouri, wherever she measured, is flowing at 4960 CFS. Exactly 1 mile downstream, somehow she measured at the exact same time, and she got a flow rate here of 17,840 CFS. This is a 1 mile stretch. I'm actually going to change my drawing a little bit. So this is like right at the confluence. So they like they meet right there, but these rivers keep going this way. Okay. Is the river rising or falling, and how fast? So we're going to assume the river has a width, this whole thing, even though I drew it kind of shrinking, but we're going to assume it has a width of 300 feet. So is the river rising or falling? Probably need a calculator to figure that out. What do you think?
Rising.
How can you tell?
It seems like the flow is increasing.
Yeah, because there's more water coming in than is leaving. Right. And so, and if you wanted to know how fast, I'll just do it real quick. So what we're going to do is it's rho Q in equals rho Q out plus the accumulation. So D by dt of rho V. So that's the mass, right? And so what we're going to do here is we note that it's all water. So these rho's go away, right? And then I gave you this, I basically gave you the volume by saying, look, this is 300 feet wide by a mile this way. So we're going to kind of pretend it's a rectangle. Really, it's a swervy, it's a river. So really, it's kind of like a, so if you can call that a rectangle, but it's a pretty good guess. If we said this is 300 feet wide by 1 mile long, right? It's pretty safe to say it's pretty close to a rectangle. And so then what we'll do is we'll say, okay, well, Q in is 13,770 CFS plus this one, 4,960 CFS equals this, what's leaving right here, 17,840 CFS plus, and for that volume, what we're going to do is we're going to take that area because it's not changing in time. We're going to pull it out. So that's 300 feet times a mile. So that's this, that's the area of the top of this thing. Right. So whatever that is, 300 feet times 5,280 feet. That's the mile. And then we're left with dH dt. And then we can solve for dH dt. Okay. And I don't remember what the answer is, but that's how we would solve this.
Right.
Can you see it? Can you see there's quite a few assumptions that were made here that make this kind of make this wrong? Can you think what a few of those might be? Aside from the fact that we're assuming the shape is a rectangle, which clearly it is not.
Yeah.
Anything else?
You
have to think about how rivers work. I don't know how much you know about how rivers work.
Not much.
Okay. Well, there's a few things. So the shape is the area, the vertical shape is a rectangle. But the other thing that we're assuming is that, like if we were to look at the cross-sectional area could have a shape like this.
Oh, okay.
So then the hill slope kind of goes up like this, right? So the higher it rises, the more area it has. As it rises, it's going to take up more space. Almost all rivers work this way. Okay, so then the cross-sectional area is rectangular also, okay, which clearly is not. Okay, something else. What about evaporation?
Oh, yeah.
Is that an in term or an out term?
Out.
Out. That's an out term that we didn't account for. What about groundwater? You like soil science? Do you think that rivers and the soil communicate with each other? Do you think like water goes back and forth?
Yeah.
Yeah, definitely does. Now, we don't know if it's a loss term or it's a gain term. Usually though, if the river is rising, you would think that usually if the river's rising, then the water is leaving towards the ground. And if the river is falling, then usually you've got wet ground that is feeding the river. So like, if here's a river, so here's the river and it's flowing into or out of the board, then let's suppose this is all sand.
Yeah.
Then what happens is the water table is kind of like this inside the ground. So let's suppose it's at complete equilibrium. So there's no changing, right? So if it looks like this, can you picture what I just drew for a river?
Oh yeah. Yeah.
Okay, so then what happens is, let's suppose the river level drops, like all of a sudden, it drops down to here. Okay, so now what happens is all this water is going to start to kind of come out and it's going to flow into that river. And really what's going to happen is the pressure here is higher than the pressure here. So the water is actually going to flow out. You're not going to see it. I guess there are times and places where you would see it, but really it's going to flow like that. On the other hand, if the river were to suddenly the flow were to like, I don't know, we were to get a big flood and the river water is higher than what's in the ground. Well, now the pressure here is because the water is now deeper here than it is right here. So we get a pressure gradient and it's going to drive the water this way. Okay. Or in this case, like it's actually just going to flow straight up through the ground. So it just kind of depends. But the groundwater can go in or out. It's just kind of, it depends on a lot of things. Obviously, this is a vastly simplified drawing, but so it's something that I realize like a lot of my students, because I've spent so many years thinking about these things, I realize like my students never think about these things. So anyway, so we're about 5 minutes over, but any questions?
Yeah. So how do we know that we that the water level was rising in this case?
Oh, right. So actually we know in this case that it's falling.
Oh, fall. Yeah. How?
Well, there's two things we can do. One, we can solve this equation that we just created, and we're just going to look at the sign, whether or not we're getting positive or negative, right? The other way, and this is basically I'm comparing what's coming in to what's going out. And if I add those two things going in, I get 18,730 CFS. So every second, 18,000 are flowing in and 17,000 are flowing out. So it has to store water. So the accumulation has to accumulate water.
Right.
Right, it has to be positive. And so if we solve this equation, we've got that 18,000 right here, got the 17,000 here. So this is going to be a positive sign to balance the equation, and we're going to have a positive number. Okay, and I think, let's see, let's go ahead and get the answer for you just because, oh wait, I don't think I put this, I don't think this is in my key. Well, that would be annoying if it's not. Oh yeah, it is. Okay, so when you solve for it, dH dt equals, let's see here, 0.00. Again, you would expect a small number. But again, I made these numbers up. So there's really just no question. 187. This is feet per second. Oh. So you might see that and you might say, is that fast or slow? What do you think?
Slow.
Seems slow.
Per second.
But it's feet per second, right? Like if it was like if it was 1 foot per second, that would be like terrifyingly fast, right?
Yeah.
So I converted this because I was like, well, those are just the wrong units for this, right? So we converted it to 2.02 feet per hour. Fast or slow?
That seems pretty fast.
It seems pretty fast, right? And again, I just made these numbers up. So, could be, but I mean, a river could rise that fast, certainly. And flash floods, the ones that like capture people, they'll rise at least this fast. They'll rise faster than this. In fact, I almost got swept away by one. You think like, I spent my whole life studying water and water physics. You would think I would be too smart for it, but I went and stood on a rock right in the middle of the flash flood area, and the water probably rose a foot in 15 minutes. So I guess that's, twice as fast as this, and it almost got me. So that's interesting.
Yeah.
Huh. Why is your screen frozen here? What's going on here? Anyway, well, know that number equals 2.02 feet per hour. I wrote it on my screen. It's not showing up in yours. Oh, it's probably from when I accidentally hit the button. Anyway, that's the end of it. So anyway, I hope you have a good day. And any other questions?
No, that's all.
No, but this is kind of interesting, right? I mean, it's like, I never think about how rivers rise. It makes sense. Like, obviously when it rises, because that's the other thing. If it rains, you also get a source here that we don't account for, which is like on the surface of the river / water that just runs down the side of the banks into the river. Like in the case of the Mississippi, in New Orleans, that's almost nothing because the levees are right up against the river. So the only part that like flows directly into the river, like at New Orleans, is what lands on the river from the top of the levee down to the river, which isn't really a whole heck of a lot of space for a river of that size, So I don't know. But, so most of what we see in New Orleans of the river rising and falling is because there's more water or less water flowing from upriver, which is because it rained or snowed somewhere upriver. So, yeah. And there's probably not a lot of groundwater because all that groundwater that we get in New Orleans is coming from what's inside the levee. It's like, well, that's not very much land. So, yeah. Anyway, so hopefully this was helpful, and I will post a recording if anybody wants to watch it.
All right, cool.
All right, Max, take it easy. Good to talk to you.
You too.
And good job with the calculus, man. I'm impressed.
Thank you. It's been like a year, so I was having trouble trying to remember how this.
Yeah, but it's also like what's most important to me is just understanding, like, okay, d rho dt, what is that? Dh dt, trying to apply the concepts rather than, let's solve for the integral of y to the 1/2. Well, those things, we can always look that up, right? So anyway, all right. Anyway, I will talk with you later.
All right.
All right. Take it easy.
You too.
See ya. Let's see. How do I end this meeting? Oh, it's up here. Stop share. Oh, there's my ugly hat. Which I wear because I have this COVID haircut. I wish I could tell you a funny joke right now. For those who make it to the end. What's my new funny joke? Oh yeah, how come you don't see fat ninjas? Fat ninjas are the best ninjas. All right, hope you're having a good one. Take care of yourselves.